All right, so let's wrap up our discussion on superposition. Actually, we didn't even get to superposition last time. We talked through an example on 2D separation of variables. It was a little bit more complicated. But if you remember, what we did was we said, all right, there's this problem that we're looking at. We can actually do a substitution and say that there's this variable theta. And theta is just the difference between temperature, T, which is a function of position, and some reference temperature, say T ambient or T infinity. If we make that substitution, then we have a case where the boundary conditions in one of the directions, the x direction in our example, became homogeneous because the temperature went to 0 relative to the reference temperature. And then on the other hand, we had convection, and that was relative to 0 as well, right? The 0 temperature. So we kind of, had this problem where it worked to have the substitution give us one direction. Now in this problem today, what we're going to start with is a problem where that doesn't work, where no matter which direction you have, the boundary conditions are not homogeneous, and there's no simple transform that you can, or simple substitution that you can introduce that gets you to a homogeneous boundary condition in one direction. All right, so let's look at this example. Okay, here we have, again, it's our rectangular domain. On the left-hand side of X, over here, we have some specified temperature TL. On the right-hand side, we have TH. Okay, so right away, you can see these are not homogeneous, right? Their actual temperature is not 0. And then in the Y direction, we have a specified heat flux. So that's not homogeneous. And we have a specified convection, which is, again, not homogeneous. It's relative. There's always a piece left over that's not directly multiplying temperature or its derivatives. Now, in the previous problem, we just said, okay, let's make the substitution where T is equal to T at this boundary minus this reference temperature, TL. Okay, if we did that here, we could try to do that again. But on the right-hand side now, we would have a different reference temperature. Right? There's a different temperature over here. So that is not 0. So you can't get both of them simultaneously to be homogeneous. And that's the problem. So what we're going to do now is basically the same thing we did before, but we actually can break the problem into two subproblems. One is a problem that's homogeneous in X, and another that's a problem that's homogeneous in Y. And again, because this is a set of linear PDEs, the problem is linear, meaning you can add the pieces together. We can break it up, solve the problem separately, and then add them back together. Physically, what that means is I'm saying I can break my temperature into two different temperatures, solve those temperatures separately, and add them back together. Okay, so for this problem, here's the statement of the boundary conditions up here. Right? We have our PDE, same PDE as before. Here's our boundary condition x equals 0. Here's our boundary condition x equals w, not homogeneous. And here's y, right? This hopefully makes sense to you, and these are things you could come up with on your own. Okay, so what I said was superposition, right? We're going to take a solution T1, we'll call it. That will be a solution that is homogeneous in the x direction. Okay, so non-homogeneous in y. And then T2 is the opposite problem, and then we'll sum those back together. Okay, so the main, I guess, trick here, or the challenge, is to come up with these boundary conditions that are homogeneous. So like, how do you go from what we have now, which is not homogeneous, to a homogeneous problem? Okay, so the rules that you follow here, just sort of wrote them out. It's a little unclear what I'm saying, but the rules of how you get homogeneous versions of the non-homogeneous boundary conditions are, three things. First, if you have a temperature, so let's say we're picking the problem to solve first is we're going to make the y direction homogeneous, and let's solve the x problem first. Okay, so how do we make the y problem homogeneous? Well, we would have to come up with two boundary conditions that represent these types of boundary conditions, but that are homogeneous, sort of homogeneous versions of these. So let's look at Q dot first, right? What's the homogeneous version of that boundary condition? Right? If we're saying the dt dx is equal to something at that boundary, what would the homogeneous version of that be? It'd be where q dot double prime is 0, right? Adiabatic. That's the homogeneous version of that boundary condition. And what's the homogeneous version of the y equals w boundary condition? Well, it would just be convection where T infinity is equal to 0. Right, so you have T up there at the boundary, the temperature of the domain at that boundary, relative to when T infinity is 0, and that's a homogeneous boundary condition. So we would make those two substitutions or changes, I guess, to the problem, and then solve the x version of it. Okay, then we come back and we have to do the second problem where we'd say, what's my homogeneous version of a temperature boundary condition? Well, that temperature has to be 0. So we'd say TL is 0. And we'd also say TH is 0. And we'd solve that problem with the y conditions as they are, and then add them back together. Does everybody understand what I'm saying there? Makes sense? Yeah. Because we still want to have convection, right? So what you're saying is if we had Ty or T at y equals H equal to T infinity, then that's just saying that it's 0, that heat transfer is 0, right? No, so homogeneous doesn't mean that heat transfer is 0. It just means that the equation that you have is not a function of some constant or something that's not directly multiplying your temperature and its derivatives. Okay. So yeah, it's not definitely not saying 0, because you could have right. So let's say temperature was 0, you could still have heat transfer there, right? You still have Q dot or heat transfer across that boundary due to convection or something, even if temperature is 0. So it's just a way of stating the boundary condition that gives you that satisfies the homogeneity requirements. Yeah. Yeah, it eliminates anything that would end up on the right-hand side. So like here, this is a constant, and if you evaluate this stuff out, you'd end up with stuff on the right-hand side, right? And anything that's left on the right-hand side, that has to go away. So all these substitutions we're doing are trying to get to that point of having it be homogeneous. Yeah. I think so. Yeah. I mean, it's saying that mathematically we can separate this out, solve it, and then bring it back together because of the special properties of the PDEs that we have. And if we can get the boundary conditions to follow the same set of properties, then we can separate things out, solve it, and then bring it back together. If you have a nonlinear PDE, or you have nonlinear boundary conditions, meaning like you have a boundary condition where temperature is the product of, some position X times some position Y, right? So if it's not a simple domain, basically, it's not along a constant value. Right? Yes. So essentially, it's a really laborious process because you have to solve separation of variables twice. You still have to do separation of variables. You just have two problems you have to do that process on. Okay. So let's look at actually how that plays out. It's a good segue. So here we have our original problem restated on the left-hand side. So how do we actually come up with two equivalent problems that we can add back together that give us our solution? So first thing is, right, let's get the PDE. So let's say first we're going to say dt1 or d squared t1 dx squared, right? That plus d squared t1 dy squared is equal to 0. That's our PDE for the first problem. We're going to come up with a solution for t1 and t2. Let's do the second here. So d squared t2 dx squared plus d squared t2 dy squared equals 0, right? So those are the two PDEs that we have for our new problems. We'll just naming the variables here. Let's see. Okay, and then so let's come up with the boundary conditions. First, let's say let's make the x direction homogeneous first. So looking at our boundary conditions in x, what do we have to do? We have to take this temperature here at x equals 0 and set that equal to 0. That temperature has to be 0. This temperature also has to be 0 on the right-hand side. Okay, and then our y boundary conditions remain the same. They're unchanged. Okay, we're going to solve for the non-homogeneous y first. And so that down here was just q dot double prime. And then up here on the top, we had h bar t infinity. H bar t infinity. So that remains unchanged. So we could go through and we could do separation of variables on this problem now, solve this problem, enforce the boundary conditions, get our eigenproblem, solve the eigencondition, et cetera, right? You go through that whole process and you get back a solution with a set of lambdas and a temperature solution for that in T1. Okay. Let's actually just real quickly write out the statement here of the boundary condition. So T1 at x equals 0 equals 0. T1 at x equals w equals 0. And then we're saying q dot is equal to the same thing, right? It's unchanged from over here for the y conditions. Just leave that unchanged there. Okay. So that's the first problem. The second problem, okay, we're going to say now this at the x equals 0 condition. Now we're allowing non-homogeneous in the x direction. So this just stays to, TL. And over here on the right-hand side, this stays TH. Right? And then up on the top, what do we have? We have H bar relative to a temperature of 0. So T infinity becomes 0. So we're solving this. And right, if you think through that boundary condition right down here, think through this boundary condition down here, where we're saying this over here is 0, that leaves only functions that are multiplying temperature or its derivatives in that boundary condition. That's what makes it homogeneous, because we're getting rid of this non-homogeneous constant part of it. Okay, and then on the bottom, we'd say, well, this is adiabatic, right? Q dot double prime equals 0. That's adiabatic. Okay, so now we've got our little adiabatic boundary here. Okay, so if we write out those two that we changed, it was now 0 is equal to minus k t2 dy at y equals 0. That's the bottom boundary condition. And the top boundary condition was minus k dt2 dy at y equals h bar times t2 at y equals h minus 0. And then the others are unchanged. Okay, makes sense? Yeah. So, I mean, like, let's imagine a case where, so if I think I understand your question. So like, if this is our boundary condition down here that we're looking at. So this boundary condition is valid even if, like mathematically, it's valid even if T infinity is really, really small, like say close to 0. This is a cryogenic application or something and it's 0.2 Kelvin, right? This is still a valid boundary condition because we're saying the conduction has to be equal to H bar times that temperature difference, whatever it is. Mathematically, it still makes sense. So it's mathematically, it's okay to say that this T infinity is 0, like it doesn't change the nature of the equation, right? But yeah, it's going to be, see, I feel like I'm kind of missing your question. So the goal is we want to get these boundary conditions to a point where they're homogeneous, right? That's the goal. So we need something that looks like the boundary condition, but it's just a homogeneous version of it. So if you're specifying heat flux, you're specifying that Q dot double prime is equal to the conduction on the other side. That's at that surface. Q dot double prime is your incident. Conduction on the other side is what's happening on the other side. So in order to get that to be homogeneous, you would simply say, well, what's the part that's left over that's not multiplying dt dx or whatever? It's that Q dot, right? So that part that's left over, I set that equal to 0. In any equation, you'd solve it out, and any part that's left over for your boundary condition, whatever it is, that's not multiplying t or its derivatives, you have to set that equal to 0. That's the homogeneous version of the boundary condition. Okay, so then we do this, and then we add all the stuff back together, and this T infinity will come back in later on when we solve the Y homogeneous boundary condition. Yeah. Yep, and that's exactly what we're doing, and we're all the pieces that sort of tie together end up adding. They're additive, right? That's what makes it linear. Okay, let's keep moving here. So we don't have another lecture and a half of. Okay, so anyways, this is actually the fundamental concept. So you just go through and you solve these two problems now the same way we did before. You come back and then we would say at the end, T, oops, sorry. My final T is then T1 plus T2, and that's it. And then it's the only difference is it's just a lot more work. You have to solve two problems. Okay, so on the homework this week, or sorry, the homework on this, which will be next week, you will have to do separation of variables. But I want to just give you a bit of a hint. I'm not going to ask you to do superposition. Okay. So you want to convince yourself that you don't need to do superposition for the homework next week. But it's a tool that's there if you need it. Yeah. Yeah. So sorry, this is where I lose track of where I am. So if this is the one you're doing Friday, then apply what I said to this week. Okay. So I just finished putting the homeworks together a couple of weeks out. So I'm like, my mind is in 4 different places. Okay. That took a little bit of time. So let's move on. If you guys have more questions on that, please let me know. We could go through it in office hours too.